Welcome to Competitive Engineering Inc. here in Tucson, Arizona, home to dedicated leaders in engineering and provider of the highest quality service in the aerospace manufacturing industry. Come inside, take a look at our project. This is the quality inspection room. Here resides our autonomous inspection system for this gear. So on our workbench, we have our universal robotics, a robotic arm. It is responsible for picking up gears from our custom gear fixtures. Then it will place the gear on our flatness inspection, which consists of our go-cater and our rotary stage. From there, we take the gear over to our key dimensionality inspection tool. The robot is also capable of communicating with our different inspection devices to categorize the gear accordingly to the output. Our team engineered this system to precisely and efficiently automate this gear inspection process that was previously a fully hands-on.
The original process begins by inspecting the flatness of a gear. Using this angled vise system, the operator slides every gear through this gap in the vise. The gap represents the acceptable tolerance of the gear, measuring how flat it is. Once it passes the flatness inspection, they get placed on this keyinst device, which precisely photo scans each gear. The device compares them to the original 3D model and returns a detailed analysis of which features miss the tolerance range. The original process works, but it is proven to be costly and inefficient, taking up to 2 people to inspect and up to 4 minutes per part.
To automate this inspection process, we designed and built a workbench that will hold our entire system and allow the robotic arm to move freely. It was important for our workbench to be mobile and allow our components to be attached to our workbench easily. So these fixtures were a primary focus because the design of this fixture determined the hole pattern that the vacuum gripper head would descend on the fixture and lift the gear. When we were thinking of ideas on how to stack the gear, we were looking at symmetric features on this gear, and we wanted to create posts that the gear can slide down on. However, when we were investigating this idea further, we saw that the gear can be inserted in 90-degree rotations and also be flipped around and inserted. It is important to address this problem because one of the constraints of our system is for this gear to be inserted into the fixture in the correct orientation. So due to the symmetry, we were able to insert the gear in more than one orientation. So we began looking for unique features of this gear. On our next revision, we were able to find this unique slot in our gear. So we wanted to choose 2 of the original hole dimensions, but 1 unique slot. After printing the prototype and submitted it to user testing, we could see that the gear does go in as intended. However, there is another orientation where the gear can also be inserted, and this is the wrong orientation. So solving this constraint was important because when the gear is inserted in the wrong orientation, it cannot be lifted and inspected, and we need the correct orientation to ensure maximum suction. To solve this constraint, we applied the Poka-Yoke methodology to ensure that the gear cannot be inserted in the wrong orientation. So unlike this prototype, for this one we're adding 3 hole dimensions and this key post that will guide the gear to be inserted only in this correct orientation. This is the only way the gear can be inserted. Any other way will not allow it to go through. Because our prototypes were made out of 3D printed PLA, it could not withstand the robot forces that were exerted on the post, and our fixtures began to break. As a result, we upgraded to carbon fiber filament. However, that doubled print times and caused new complications. Therefore, we sought an alternative to machine our fixtures out of aluminum. For our first machine prototype, we matched the stud locations to our 5th axis holes. As a consequence, we could only rotate the fixture every 90 degrees.
We added an additional set of stud holes rotated 45 degrees from the original hole locations. In some bench locations, the fixtures were not accessible to the UR5 because of the rotation required. In order to make the fixture exchange as simple as possible for the technicians, we increased modularity in our final revision.
We now had to develop the end-of-arm tooling for our robotic arm. After speaking with our sponsors, we determined that the fastest, most cost-effective solution is to outsource a gripper attachment from Millibar. Once we received the gripper, we assembled it onto our robot and verified its compatibility with the 3D printed fixture. After fitting both gripper heads on a fixture, we concluded that the tolerance of the gripper holes is sufficient for our fixture posts. We then tested the vacuum system to determine the optimal operating condition. The assembly consists of 2 venturi pumps and a pressure gauge connected to solenoids that activate each pump. After connecting the gauge to the external air compressor, we found the best operating pressure at 55 psi by programming the robot to repeatedly lift the gear off a fixture, place it down on a flat surface, and return the gear to the fixture. This process helped us understand its capabilities and guided our design ideas for the flatness system that was previously manually operated.
To automate this system, we went through multiple trade studies and we conducted multiple designs to see which one was the best. We had an option of including probes to our vise. We also went with the option of having a railing system, but then we finally saw that we had the best option with a go-cater and a rotating stage. And this was due to eliminating mechanical issues and converting everything to digital. The reason we needed a rotating stage was due to the fact that the go-cater is stationary. And as the laser is turned on, the rotating stage rotates and captures the full surface of the gear. The software compares 20 different regions of the gear and compares those to each other to see if that is below the tolerance level of the actual system.
So in order for us to program our robotic arm, we first had to familiarize ourselves with the user interface that came with it. So here we have the UR5 user touch interface. This allows us to program the robot, move across our workbench, and as well as any necessary actions to sort our gear. This was a challenging yet rewarding opportunity for us to learn about this versatile software because it helped us to ultimately achieve our goals with the system. So in addition to protecting our engineers, the robotic arm has a force detection feature that stops the robot from moving if it encounters an obstruction. Like so. So as you can see, once it hits the post, an error pops up and stops the system entirely.
With the help of our supporting partners and our amazing sponsors, we were able to successfully automate the manual inspection process for the machine gear. Comparing the before and after the gear inspection, we can see improvements in different areas of the process. The most important outcome is the total output of the system. Before, a technician could only complete about 100 gears per shift. With our system, we can easily complete about 280 gears per shift. This is huge for competitive engineering because it improves on their downtime, making the process more efficient, more cost-effective, and now they have an increased capacity for the gear inspection process. Our team was honored with the opportunity to work on a project that solved a real-life manufacturing problem. We used our expertise in lean manufacturing, programming, and modeling to deliver solutions that support our sponsors' vision for the future of CEI. They seek to implement automation in different areas of their manufacturing facility to remain competitive in the modern world. The automation manufacturing team developed an outstanding system that not only solves the gear inspection problem, but is also a project that will drive the company forward.